Okay, working on this line 6 spider valve 112, and I'm going to take a look at the bias and then take it a step further and do some comparisons by looking at the total harmonic distortion and see how that compares to the default bias. So my plan is to just get a baseline with the recommended default settings for bias and then adjust the bias while monitoring the total harmonic distortion, and then I'll do a sweep through the frequency range and measure the total harmonic distortion at multiple frequencies. So I have the signal going to the input here, and then the output is just feeding a load resistor of the same value that it expects for the speaker. Now, to do this process manually with the instrument would be very time consuming, because you'd have to set it up at each frequency, make a measurement, save the value, or the next frequency, repeat the process for every frequency point that you want to capture. So I created this LabVIEW software, which is a very common software used for controlling instrumentation. And I've got it connected to a USB port, and then there's a device, a GPIB device, which communicates with the instrument. It's kind of an interesting programming language here. It's basically graphical, so you have all these lines, and it has a similar layout as schematics, so it gives you some familiarity when you're trying to code this way. And I have it set up so I can save files, create files. So I already created one for this project. And the first test I'm going to run is bias and harmonic distortion. And then I'm getting set up for the baseline measurement, so I've got that written in as the trace name. And then I have this set up for 100 millivolts and 1 kilohertz for frequency. And then if I select this, it'll send the command to the instrument. So now the instrument has received that and it's set up for that level. And then I can also select the resolution, how many data points I want. The more you set, the slower it goes, so it's kind of a trade-off. I'm going to start with 5 while I get things set up, and I might increase it later. And then the measurement I want to take is actually distortion percent. Okay, so I got the instrument on now. Got a little bit of signal going through. It's measuring 2.5 volts. That's across that load resistor right now. And that frequency measurement, 1001.5 hertz. Then on the oscilloscope, which is also connected to the load, you can see the waveform here. I have an RMS voltage measurement there on the bottom. I'm going to see what point it starts clipping. So right about there. And that's about around 18 volts. And I kind of want to run this test at a somewhat realistic volume, so I probably won't do anywhere near that. The other test I want to do is check different frequencies. Like here it's clipping at 18, but another frequency it might clip different. So I'm going to jump up to like 10 kilohertz and see what it looks like. Okay, and here's 10 kilohertz. We'll zoom in, and that's not clipping, so we should be okay there. And I'm going to jump down to like 100 hertz. Okay, and 100 hertz looks okay as well. I'm going to go down to 20 just to look at it. The transformer might have issues repeating 20 hertz. And to do that, I just go here, type in 20, hit enter. It sends the command for 20 hertz. Looks like 5.2 volts. And here it's way zoomed out or zoomed in, so definitely not a pure sine wave at 20 hertz. And I have noticed with this instrument, if the signal level gets too low, it has a hard time even making a measurement, and then the software doesn't want to work right, or the graph just looks goofy. I just wanted to note the power level that it clips at. So around, it's a pretty gradual clipping, so you could say I start seeing it about here, a little more obvious there. And I think a lot of the old Fender schematics or documentation shows measurements at 5% harmonic distortion, which I could actually do quick here. So I'm going to go back to the generator. Okay, so I'm on manual control here. I just reset it up, so I've got a set point of 1 kilohertz, amplitude is 0.1 volts, and right now I'm measuring 14.4 volts. And I'm going to switch to distortion. So this will be in percent. So right now that's 0.7. So I'm going to bring it up to 5%. So right about there. And then take a look at the waveform. And we'll look at the RMS voltage, which is about 18.8. And then from that we can calculate the power. So calculating it out, you have power is voltage squared divided by the resistance. So we know that's an 8 ohm resistor. And then we have 18.8 volts squared. And that gives you this. So you end up with 44.2 watts. And for this test I'm going to run about 12 volts, and that gives you about 18 watts. That'll keep it from clipping at 100 hertz and 10 kilohertz, and hopefully everything between. Okay, the first thing I'm going to do is get a baseline of the instrument itself. So I have the output connected to this coupler feeding directly into the input, and then I'll sweep through the frequencies and grab the total harmonic distortion data and graph that. And I'm just going to click run. Now let's send a command to the instrument, and that's starting to run. And then this preview graph will show the data as it's going. And then once it's done, we can go to the second tab, which will show the full graph in a bigger view. And this auto scales in real time, so it looks more extreme than it actually is. Okay, and here's the instrument itself while it's running. We're at 8 kilohertz, 13 kilohertz, it's almost done. And there's 20 kilohertz, that's the last step. So the software captured the data. Now I can go to the graph tab and look at it. And you have to keep in mind that this auto scales, so it's 0.0195 and up to 0.023. So all these values are very low distortion. So as soon as you plot anything with, say, 1% distortion or some higher value, this will probably look like a straight line. So this should be good enough for a baseline. And it just confirms the instrument doesn't have some major problem where it would actually be giving false readings. So I'm going to save this trace. And now any trace we add will be in comparison to that one. Back in the amp now, I'm going to set the default bias, which is 35 millivolts. So I've got a voltmeter off screen here. And then these points to probe here are labeled H4, which corresponds to 2V3, and then this control here. So now I'm just going to adjust this while looking at the DC voltage on the multimeter. It's a little touchy. Right now I've got 35.3. I'll switch to the other side now. Adjust this other one. 35.4. Okay, and here's the measurements. That's tube V3, 35 millivolts. And then tube V4, which is 35 millivolts. Okay, now I've got the amp set up. Same levels, same frequency ranges. Change the name to a 35 millivolt bias. So I'll run this. You can see already there's 2% distortion. Down to 1 something. Gets into the higher frequencies, you can hear it through the transformer and the load resistor. Okay, and that one's done. Go to the graph here, and I'll save it. There's also a cursor here you can move around to measure points. So around 1 kilohertz we have about 1% distortion, 0.85, and then as you get higher it goes up quite a bit. But this is, a lot of people can't even hear this range anyway. So fairly low distortion as it is, it looks like. For a tube amp, at least, tube guitar amp. So it looks like we're generally in the 1 to 2% distortion range, if you ignore this upper thing. So next I'll bias it based on the distortion at 1 kilohertz, and then run the sweep again. Here's another LabVIEW tool. I kind of made it look like the instrument and perform like the instrument, more for just manual control. So I can set distortion again, set the amplitude and frequency, and now I'm gonna adjust the bias and watch this reading here and set it for the minimum value. And I actually have to click continuous read here, otherwise it's just going to hold that last value. Now it's continuously pulling the instrument, getting new values. And I've already adjusted it so it's gone up. So it looks like I need to go the other way. So I'm adjusting V3 right now. So now it's going back up again. So I'm going to adjust it the other way again. So 0.55 is about as low as we're going to get with that control. I'm going to the other one. Now I'm on V4. So one of these will control the upper half of the waveform, the other will control the lower. Now I'm going up again, so I'm going the wrong way. .48, 0.46. The measured value updates fairly slow, so it's a little tricky to adjust this. So 0.45, that's probably about as low as I'm going to get. So I'm going to leave it there. I might go back to voltage and see how much that changed it. So I'll select measurement, AC level, 12.83. So I might bring the amp down just a little to get that back to 12 volts. Okay, so we're about 12 volts there. Now I'm just curious if that affected the distortion level, distortion percent. Read that again. 0.39, so that lowered it even a little more. Turn off continuous read. Then I'm going to stop this, go back to our main software. Then I'll name this lowest THD bias. And then run. First data point was 19. But 20 hertz, it's very unreliable, so I'd probably discount that. And okay, that's finished. Go to the graph. Save it quick. So the green one is the new trace. And looks like it increased the distortion below 100. But again, it's hard to say how much value you should put into that. And there's probably not too many data points in here. I could increase that. Let's scale down to the range from 100 to about a 10K. So I'm going to set the peak distortion level at about, let's go with 5 and see how that looks.